Hello, today we're going to talk about nitrogen trifluoride, and we're going to compare the VSEPR geometry to the quantum mechanically optimized geometry of a nitrogen trifluoride molecule. Here we see the VSEPR geometry of a nitrogen trifluoride molecule. It is trigonal pyramidal, which is what we would expect given our knowledge of VSEPR theory and the number of charge clouds and how many of those charge clouds are lone pairs. The bond angles are roughly 109.5 degrees, which is what we would expect here. Compare that to the optimized geometry using quantum mechanics. You might not be able to tell, but the fluorine atoms have been pushed further down. So if the lone pair is up here, it has pushed the fluorine atoms even further to the other side of the molecule. The green is the fluorine, by the way, and the blue is the nitrogen. So when we measure these bond angles, we're expecting a smaller number, which is what we get. We get 102.492 degrees, which is smaller than the 109.5 that we got in the VSEPR theory geometry. This is because the VSEPR geometry does not account for differences in electronegativity in the bonding atoms. It assumes that the repellent force between a lone pair and any given atom is the same, and that's not necessarily the case because all atoms have different electronegativities. So in this case, the repellent force between the lone pair and the fluorine atoms is stronger than VSEPR theory accounted for. Now let's look at the dipole moment. This is the VSEPR theory geometry of nitrogen trifluoride, and we see that there is a dipole moment, but it's relatively small. You can barely see the stem of that arrow right there. Compare that to the quantum mechanically optimized geometry. The arrow is a lot longer because the fluorine atoms that are highly electronegative compared to nitrogen, they've been pushed further to that side, so the electrons are going to hang out, so to speak, more on that side of the molecule. Now let's look at the energies of these molecules. So the VSEPR geometry has an SCF energy of negative 352.4065 hartrees, or negative 925,243 kilojoules per mole. Compare that to the quantum mechanically optimized geometry, which has an SCF energy of negative 352.43810 hartrees, or negative 925,326 kilojoules per mole. If you haven't quite done the math yet, that means that the difference in energies is 103 kilojoules per mole, and the quantum mechanically optimized geometry is more negative. So the absolute value is greater, but the SCF energy itself is more negative. This means it is more energetically favorable, and it's going to be closer, we would expect, to the molecule as it behaves in the real world instead of like just a simulation.